Right. Our next speaker this afternoon is Damien Tessmer, who's joined us from San Diego State University. Damien's been working this summer with James, and he'll tell us about their project together, origin of the elements revealed by equilibrium chemical evolution.
Thank you for the introduction, and thank you everybody for being here today. So why do we care about the elements? Well, first of all, they're kind of the building blocks of everything we know. And to know the time scales of metal production will tell us about star formation, which is a big question mark in the field. There's a lot of pieces to chemical evolution. They're like a puzzle. They all fit together in a way with, star formation history and enrichment sources kind of adding together to create the observed abundances. As you can see on this figure to the right, we have a periodic table sorted by the different ways that elements can be created. Big Bang, the big ones that we focus on in the city is Big Bang fusion. This exploding massive stars, also known as core collapse supernova, and then this is type 1a supernova right here, exploding white dwarf stars. So classically, it is believed that as stars live their lives, they create more metals, and then when they end their lives, they put those metals back in the interstellar medium, enriching it for the next generation to be born with more metals. That's kind of seen here, where we have it's radius dependent, and the model also suggests that it's also time dependent. So we have here the oldest stars with the lowest amount of iron, and then as they get younger, there's more and more iron. But when we actually look at data, this data here is from Sloan Digital Sky Survey 4, we see that the dispersion is nowhere near that great for different ages, and beyond just the oldest stars here, they seem to fall into like a single pattern. So why? Why do we think it does that? James is working on this paper for something called equilibrium chemical evolution. It states that the equilibrium metallicity, which is just radially dependent, has nothing to do with age. It just settles into this after a certain time. And a direct implication of this theory is that we can use solar abundance, or we can use abundances to solve for yields, which otherwise are very difficult to solve for. My data comes from Sloan Digital Sky Survey 5. It is a multispectral imaging and spectroscopic redshift survey. They use a 2.5 meter wide angle telescope. It has a very large field of view, so they're allowed to capture a lot of stars. My sample is actually 420,987 stars, red giants. It's in Apache Point, New Mexico. And I'm using Milky Way Mapper program, which it uses two instruments. You have BOSS, which is a resolution of around 2000, which is low, and it's optical. And we use Apogee, which is like medium resolution, 22,000. It's near IR. So now here are the elements I actually have in my study. I hope you guys like this figure because I'm going to be using it a lot. I have 18 elements. They can basically be divided into three categories. So first we have the elements that are core collapse dominated or core collapse only. We have this group here, which has some core collapse and some supernova type A. And then we have these guys down here, which are just neutron capture. So I will be using magnesium as my tracer for metallicity. It is core collapse dominated, so it's a very clean indicator of like a specific type of occurrence. And then I will use the iron to filter between stars that have a supernova 1A component and stars that don't, because the ones that do are younger. A quick little chemistry side note. So every star goes through this process called the alpha process. It starts with them. They're making their hydrogen into helium. And then once you get 3 heliums, you can make a carbon. And then you just add, there's a lot of heliums to stars. So you just add a helium and you can keep going down this line. And basically those every other, so it's just 6, 8, even proton numbers. All of these are alpha elements. They're expected to, in some point, be present in every single star, depending on how old they are. So I will be filtering I did filter my data between high alpha, which is also low type 1A, and low alpha, which is high 1A. So my data was given to me in the form of hydrogen. So using this, I can change it to fit my needs. In this case, I'm plotting iron on the bottom. So this is just mixed metallicity, and then Mg over Fe, which the top part here would just be that created from core collapse. And then down here has mixed enrichment. So this is going to be our older stars. And then this is going to be more indicative of the trends we're actually looking for. So for every element, I started with a density plot. So first, this is metallicity, my tracer Mg on H. The element here This is titanium. I just picked this one because it looks pretty. So this is the calculations I used here. So starting with the density plot, the darker means there's less stars. Some of these just have one in them. And then as you get like lighter, there's like a higher concentration. And then once I had the density plots, I chopped it up into a bunch of like long ways rectangles and picked the best point from each one from the mode. And then once I had those modes, I best fit the line. You know, as with all data, more data equals better results. And the majority of my data will fall between this 0.5 and like 0.3 area. So my elements can be divided into generally 3 categories. This is really preliminary. We're not going to know a lot until we have the results, but just, you know, how we decided to do them. So for core collapse dominated alpha elements, we have, you know, oxygen and silicon. We expect them to be roughly flat. Like oxygen is created in the same way that magnesium is, so it should be about the same. And then silicon core collapse should be about flat. Right, elements near iron and type 1A or iron core collapse and type 1A ratios should look similar to iron. So we hear calcium, chromium, iron, nickel, they're all, you know, in the same category. For the most part, they have this like wave to them. They kind of go up. Chromium is a little special, or calcium is a little special because, you know, that one just has a lower. Elements not acting as expected. So typically odd elements, because of the way they are formed, we would expect them to be metallicity dependent. For instance, let's talk about aluminum. So aluminum happens, or so we think it happens, when you have a bunch of magnesium and then they capture a neutron, and that neutron beta decays into a proton, giving you this 13 near aluminum. So you would expect that with more magnesium, aluminum would go up, but aluminum actually just kind of flattens out. And the same is true with potassium, although we do not have argon, so I can't say for sure. Elements with mixed enrichment, once again, we kind of expect them to look like iron, but titanium and manganese go a little bit further and just have like this straight up dependence. Like they're just strongly correlated. They just go up. They may not like look that much different from iron before, but the axis on this is actually twice as big as the iron plot one you guys saw. And then sulfur, strangely, just has this inverse metallicity where it's actually going down as we're increasing the metallicity. Sulfur's right here. And then for cerium and neodymium, we don't really have like a clear like idea of what we want them to do. They don't really have any, you know, core collapse or supernova things, so they shouldn't really have a pattern with Mg, but they're still interesting nonetheless to have. Speaking of those same two, we don't necessarily know if the results are good. This is kind of like a lot of a spread here. So, you know, we'll take this trend with a grain of salt. Cobalt and sodium are known prob children for SDSS. So here we again have this like large range here. There's a lot of coverage here. The line still looks nice, but it's like it could be better. And then finally, we have phosphorus and vanadium. Both phosphorus and vanadium have this here. So this multiple loci. So it appeared that they're looking for multiple wavelengths to try to find this, but the best fit line still does kind of look all right. But it just having 3 for each of them just doesn't make the data as clear. So what do we want to do with this data? We want to turn it into yields. So, you know, this expression looks a little intimidating at first, but we're going to go through it one at a time. So starting off, we have the core collapse and type 1A yield ratio of a given element X. That's what we're trying to solve for. Next, we have the core collapse to type 1A ratio of iron. This is the only assumption we're making in this entire thing. Everything else will be driven by data. We're assuming that the ratio is 40-60, 2/3. So A1 alpha is the star formation history of that one specifically is our sun. This one is calculated through data, and we get a value of about 1 at our sun, so 1.008. And R is the radial location is relative to the galaxy center. Just goes right here, you know, at our sun, it would just like even out. And then finally, these here, the gradients of the different lines will be the slopes of the trends I had on the previous slides. And this is taken also directly from observations. So next step, once I have those yields, I'll start actually comparing it to different models to see where the models hold up, where they're lacking. And then, so my conclusions, you know, equilibrium chemical evolution implies that the trends of the elements are driven by nucleosynthesis. They're radially dependent. We can infer those trends by using the data. The most interesting cases we have are aluminum, potassium, magnesium. No, that's manganese, sulfur, and titanium. And then we can map these trends to implied ratios and compare with stellar evolution models. And that's it.
Great, very nice. Questions for Damien? Izzy?
Where do you get your implied ratio?
For
Like you said, that's 2/3.
oh, it's just I'll show the picture real quick. So here we have, like right here, this is pretty much where we're getting it from. I mean, that is also mathematically proven, but I didn't like look at the specific paper to get this number. It's just kind of, I'm taking James's word for it.
Other questions? Anna?
I have a question about uncertainties on the metallicities.
Mhm.
So when you showed those 2D density plots of and your pits, it sounds like, yeah, the question is, were the uncertainties on the individual measurements of abundances in these stars taken into account when fitting these trends?
We did not use the uncertainties yet, but we plan to do that later.
Any other questions for Damien? Great, very nice job.
Thank you.